In this video, we're going to talk about the sunflower lemma in the extremal set theory. So what is sunflower? Sunflower of size R is a family of sets A1, A2, AR such that the pairwise intersection is all same. Okay, so in the picture, if this is A1 and if this is A2, okay, I should draw a better way. So if this is A1, A2, A3, A4, A5, so it really looks like sunflower. Of course, I shouldn't have any elements there. So this together with that is A1, and this together with that is A2, and this together with that is A3, and this part together with this is A4, etc. So collection of sets where the pairwise intersection is exactly equal for all ij is called the sunflower. And this is very useful tool for many extremal problems and algorithms. It has many applications. And you can guess that the name comes from the actual picture of sunflower. This looks like sunflower. And Erdős and Rado proved in 1960 that if you have many sets of same size, then you must have a sunflower. There exists a function fkr such that every family of k sets, k set means a set of size k, right? Sets with k elements, right? K sets with more than fkr members. So if you have many sets more than fkr members, contains a sunflower of size R. Okay, so many sets, no matter where you take it. Like we didn't say that the sets are from 1 up to n. So the function is independent of the union of these sets, right? It only depends on k and r. Okay? So for instance, if you have many sets pairwise disjoint, that is also sunflower because intersection is empty. And the proof is simple induction. So we proceed by induction on k. So if k is 1, what does that mean? Then you have a set of size 1, right? So you have singletons. When do we have a sunflower? If you have same element more than, if you have same element r times, then that's a sunflower. And otherwise, no element is more than r of them. So then each element is in at most r minus 1 of them. So if you have many sets, namely r minus 1 times r minus 1 times r, no, r minus 1 times r minus 1, let's see, yeah, so oh, yeah, right, so maybe it's better to, yeah, let me change the wording a little bit. For the applications, typically it's better to say distinct k sets. So you don't want to collect the same set I mean, it's okay. I mean, this is not a big constraint. So that if every set is distinct, then you take f1r to be just r minus 1, right? So then no matter how you take r distinct sets of size 1, then you're going to have a sunflower of size r. So that's the easy case. So we may assume, right? So this is when we have r sets, then this is a sunflower because the intersection is empty. If k is bigger than 1, then what can happen, right? So let a1, a2, t be a maximal subcollection, subfamily of pairwise disjoint members. Okay. Maybe it's better to have a name. So let F be the family. Now A1, A2, AT. The pairwise, I mean, these sets are pairwise disjoint. So this is a sunflower. So if t is bigger than r, then if t is at least r, then we already have sunflower of size r. So we may assume t is less than r, right? Now what we're going to do is take a union of all of them. Let A be the union of AIs. So here's an A. Now we know that any member of F intersect A because otherwise we could increase T. And size of A is at most r minus 1 times K, right? Because each AI has size K and they are disjoint sets, so that's it. Now for each element in A, consider f of A, which is the collection of, for every member in F, if X contains A, then we take all the members. So here's an A here, right? Now I look at all sets containing A and remove A, and then FA is a family of sets of size K minus 1. Now if FA has a sunflower, of size R, then F has a sunflower of size R, right? Simply by adding A. So that means by induction, we may assume FA has size at most FK R, K minus 1 R. So this means that size of F is at most the number of elements in A times F of K minus 1 R, and size of A is at most R minus 1 K. All right. So that's the proof. So there's such a function exists. So we take FKR to be r minus 1 k f k minus 1 r recursively. So what is this function? It's easy to see that this function, right, you are multiplying r minus 1 k times yes, because when k is 1, this was r minus 1 k times, and then we are multiplying k factorial, right? So k minus 1, k minus 2, etc. So it's k factorial. So that's the bound. So bound by Erdős and Posa. All right. So this is one bound, and Erdős and Posa also found the example where this function has to be bigger than something. It has to be bigger than r minus 1 to the k. Now here's the conjecture by Erdős and Posa. The conjecture is that for every r, there exists C such that fkr is at most c to the k for all k. So instead of having k factorial, you can reduce it. So k factorial is 2 to the k log k, right? So this log k factor can be removed. So that's a conjecture, and so far the conjecture, there was some progress towards the conjecture, but not very, like, this is still open, even for the case when r is 3. So the Erdős offers $1,000 for r is 3. Right? Sometimes Erdős gave cash prizes for his conjectures. There were some attempts to prove it, but the best known, well, there was some progress. Like in 1996, Kostachka proved that f of kr can be shown to be like less than some constant times k factorial times another constant. This is some function depending on r and alpha. And I'm gonna, and I didn't say what alpha, for every alpha between 0 and 1, and d is some function. And we have log k squared divided by alpha log k to the k. That was a previous bound. But then very recently in 2020, 4 people, Alves, who was a graduate student at Princeton University, and Robert and Wu Zhang. So Wu was, I think, undergraduate student at Beijing University. And they proved that f of kr is at most log k to the k times r log k to the big O of k. And soon after, so the years are actually the year that the paper was published, but actually this was done in 2019. Rao, I think he's a professor at University of Washington, improved this to the following: alpha log alpha r, log rk to the k for a universal constant alpha. And his proof uses some theorem from information theory. But still, this is not a constant. It's slow. It's a lot better than the previous bound, but still the conjecture is still open. Now let me first fix the typos here. The conjecture about the sunflower lemma is not by Eldridge and Posa, it's Eldridge and Rado. So these are the places that I fixed. Right. Now, if you look at this conjecture, it says that whenever you have a sets of size k, if you collect more than r minus 1 to the k sets of size k, then you can find the sunflower of size r, right? Now, we don't know whether this conjecture is true, but here's a weakening due to Freddy. Right? So this was proved in 1980s, so that FBA, family of sets of size at most k. Right? Now I didn't say that they all have size exactly k, but remember, no, I mean the thing is, sunflower lemma can be applied to a situation where sets have size at most k instead of equal to k, because here it says k set, but if you just allow sets of size at most k, then from 1 up to k, one of the size will have large number of sets, right? Just by using Peasoner principle. So if you have many sets, like just add f1r, f2r up to fkr, and then apply the sunflower lemma. So this relaxation isn't much different, but the main difference is that if size of f is bigger than r minus 1 to the k, which is conjectured, as was conjectured by Eldridge and Rado, then there exist R members A1, A2, AR in F such that, so if the sunflower conjecture is true, then the pairwise intersection has to be equal. But now we still don't know whether this conjecture is true, but what we can know is the following. The union of the intersections have size less than k. So that's the theorem due to Freddy. And if the sunflower conjecture is true, then this is trivially true. I mean, I should be precise. If the sunflower, we don't know whether sunflower conjecture is true with the r minus 1 to the k, but with the r, if sunflower theorem is true with this function, then this has to be true, but probably it's far from being proven. For this weak version, we can prove it. So we're gonna use induction on R. And it's if all AIs have size less than k, then trivial. Why? No, what I meant. If all x all x in F have size at most k, then it's trivial because the intersections well, why is it trivial? Well, okay, let's do the induction on R plus K, then trivial by induction, because you can reduce K by 1. So we can assume what? We can assume that there is S in the family such that the size is exactly K. All right. Now, for every subset of S, let f of x to be this, like for all A in F, and if it intersects with X, if its intersection with S is exactly X, then we take the A minus X. No, yeah, A minus X, that's the same. Then each member of f of x has at most k minus x element. So by the induction hypothesis, we may assume size of f of x is at most r minus 1 is r minus 2, because we are reducing the wait, okay, let me, yeah, so if f of x is bigger than r minus 2 to the k minus x, then f of x contains r minus 1 members, a1, a2, ar minus 1, such that the union of intersections is less than or equal to k minus x. Now what we're gonna do is, now a1, a2, ai minus 1, and ar, oh, so these things, okay, let me fix, let me add this. So remember, ai prime is ai minus x, right? For some ai in F, and let a r be the S. Then a1, a2, ar satisfies the union of intersection of these two is the most, I mean, it's less than k, because now the intersection will include x, right? One thing I should add a remark is that if x is equal to s, then this never happened. F of x will be at most 1, right? Actually, it's 1. So we don't have to worry about this situation. So that's why this s is different from any others. So you can add them. All right. So if f of x is bigger than this number, then you can always find the family of R R sets whose union of the pairwise intersection is small. Thus, we can assume f of x is at most r minus 2 to the k minus x. This is for all x. Now, size of f is equal to 1 plus right, for all subsets of So what is size of f? For all subsets of S, we look at f of x. And what is this? Well, it's upper bounded by r minus 2, k minus x. Now, this is what? This is equal to sum from 0 to k, and the k choose I, and r minus 2 to the k minus I. Right? Yes. If we replace k minus I by j, then this is the sum, so 1 plus k minus 2 to the k's power. So it's r minus 1 to the k. So that's contradiction, right? We assume that size of f is bigger than r minus 1 to the k, right? So it's a weaker version than red is the original Elgy-Shirado's conjecture. In the next video, we will talk about some application to sunflowers, some applications of the slice rank to the sunflower problems.